For this month's talk, we have Ruoqian too, a PhD student from T10's group in ICMM in Madrid. And today she's going to talk about digitized counteradiabatic quantum optimization algorithms. So whenever you want, Ruoqian, the floor is yours.
Okay, thank you, Angela. Hi, everyone, and thank you very much for joining my talk today. First of all, I'd like to thank Bei and Angela for inviting me and organize this exciting program and let me contribute to the PhD and Young Scientist Quantum Technology Networks. So my name is Ruoqian Xu, and today I will sharing my recently work with you on digitized counterdiabatic quantum optimization algorithms. So I'm now doing my PhD at the ICMM, and let's take a look at our group. Our group is novel platforms and nano devices for quantum simulation and computation. So we are located in ICMM Madrid, and our research is broadly focused on quantum simulation, and we have a strong interest in exploring new ideas and new thoughts. So coming back to our talks, I divided into 4 parts. The first part is the origin of counterdiabatic terms. Next, I will explain how we integrated with the variational quantum algorithms. And next, I pick up 3 examples to show the application of DC-QAOA. And next, I will conclude with a summary and share some outlook in the future work. So next, I will refer to these counterdiabatic terms as city terms. So before we know how CD term was proposed, we need to know what is quantum adiabatic computation. This is based on the quantum adiabatic theory, which states that the system will remain in its instantaneous eigenstate as long as the Hamiltonian of the system evolves slowly enough. But there are 2 constraints of this adiabatic condition. The first one is that the ground state will need to be separated with the other exciting states by a finite energy gap. And also, this gives the key condition for the evolution time, which is that the evolution time must be longer than the inverse of the square of the minimum energy gap. So next, the adiabatic Hamiltonian is written like this. We start with an initial Hamiltonian whose ground state is easy to prepare, and we also call it the mixture Hamiltonian. And then it will evolve to the problem Hamiltonian that we encode our problem. This S function is a scheduling function that changes very slowly from 0 to 1 during the whole evolution process. And in practical, the adiabatic computation was implemented by this totalization equation. But somehow this totalization will induce some error, which is at the order of square of the total time. So as I mentioned before, these 2 constraints gives the adiabatic some drawbacks. The first one is the long evolution time, and the second one is the error. So if the evolution time is short, then the system will be excited. And if the totalization is long, the error will be really long. So, and how can we find the balance between the speed and the accuracy? So if you picture the adiabatic process as a turtle, like this, the question can be transformed into how we can make it run faster and not fall down. So the answer we gave is the counterdiabatic terms. This term lies under the method called shortcuts to adiabaticity, and the key idea of this method is prepare, control, and manipulate the quantum states in a fast and faster way. So next, we can have a look at how the counterdiabatic term was constructed. During its early stage, Rice published several papers to construct an counterdiabatic field to speed up the adiabatic evolution, and he verified its robustness in several systems like two-level systems, three-level system, and analyzed its universality. And next, Barry proposed the transitionless quantum driving, which states that the Hamiltonian can accurately drive the evolution of a quantum system along an arbitrary adiabatic path. And this really lie a solid theory foundation for the shortcuts to adiabaticity research. And then in 2010, Qichen published papers and he proved that the invariant-based inverse engineering method is equivalent to the transitionless quantum driving. And then he proposed that the quantum control strategy that can accelerate the adiabatic process can be collectively called SDA, which is the shortcuts to adiabaticity. So this is how the early time counterdiabatic driving was established, and it can be even demonstrated in experiment. So in these two experiment papers, the first one uses the in trapped ion, and the second one used the steel rod. So these two are all following works by the Xichen's work, but the problem is that during the exploration of the counterdiabatic terms, we find that accurate CD terms can be hard to obtain, and somehow to implement in the experiment, there are many non-local terms in the counterdiabatic, exact counterdiabatic terms. So that's why we are looking for a new way, which is the approximate CD or alternative CD. And people like Antonio, Adolf Campbell, and Peter, they propose adiabatic gauge potential nested commutator, which are really, really applicable. And nowadays in many body system, we are trying to, researchers are trying to use Krylov space and tensor network to obtain much better CD terms. But as we mentioned before, only adding the CD terms to the adiabatic quantum computation cannot solve the problem that it faces, which is the nested quantum error. So the NISQ devices face some limitations like the decoherence of the devices and the limitation of the quantum qubit. Also, the circuit steps are restricted by the fidelity, and so this makes the NISQ algorithm has two features. The first one is that they are often analyzed by heuristic, and they have some traditional forms like first prepare, then reset, and then repeat. So what is the best or the most potential algorithm to have the potential to be applicable in the future? So the possible solution is a hybrid quantum classical diagram, which is called variational quantum algorithm. These algorithms are by its names are constituted by two parts. The first one is the quantum computer. Its role is, or its job is to run in a parameterized quantum circuits and also perform measurement as long as they get the optimal parameters from the classical one. And the classical computer do the jobs of executing the optimization process and finding the optimal parameters on the landscape and sending the parameters back to the classical computer. So there are mainly two popular variational quantum algorithms now. The first one is variational quantum solver, and the next one is quantum approximate optimization algorithm. The very different part of these two VQA is the design of the answers. So they often use hardware efficient answers to better implement on the real devices. And also there are UCC answers, which is unitary coupled cluster answers, which is specially designed for quantum chemistry problems. But the similarity between these two variational quantum algorithm is the optimization classical optimizer. By combining these how to calculate the gradients like parameter shift, SPSA, joint differentiation, and how to update the parameters like Adam, SGD, BFGS, Cobela, NetherMed. These two combined together can make up with very different classical optimizers and can perform very differently in different cases. So, but the QAOA is obviously natural connected with the adiabatic computation. So that's how we come up with the idea that how counterdiabatic driving can benefit this QAOA and VQA frame. So we extended the counterdiabatic terms to the end of the QAOA, which is evolved alternatively using problem Hamiltonian and the mixture Hamiltonian. By this way, we can have these three advantages, which is shallow circuit steps will effectively avoid the noise accumulated from the really long circuits, and also we can get the robustness to the noise and the fidelity of designing arbitrary circuits. So now we have already know VQA and DC-QAOA, we can take a look at its applications. So nowadays it has been applied in several fields like logistic problems, drug discovery, particle physics, molecular modeling, and optimization problems. Also combined with AI, some machine learning method, and also in solving financial modeling. So this is the first example I picked, which is a very simple problem called MaxCut. This problem is all about how to divide the edges by a cut and into two groups. So the edges are assigned with x equals to 0 or x equals to 1, and the aim of this problem is to maximize the cost function written like this. By a standard transformation, we can map this cost function into the quantum circuit spaces. So by choosing the mixture Hamiltonian as all Pauli X operators on all qubits, which in circuit basis, we apply one Hadamard gate on each qubit, and then this is the problem Hamiltonian, which is ZZ. And next, the counterdiabatic term we choose is obtained from the first order nested commutator. So here's the circuits we construct, and the result we get is obviously exciting. So the successful ratio increased from 70% to 100% when there are 4 edges present, and from 58 to 30 or 100% when 5 edges are present. This this successful ratio range is caused by the initial parameters. So let's dive into some more complicated problems like bin packing problem. So the task is all about assigning n items into m boxes and under some constraints like do not exceed the capacity of the box, or and also each item must be packed for one and only one time. So the classical formulation of this problem involves many constraints, and it took many qubits to map these three constraints into the circuit's basis. So we do not use them. We choose this quantum encoding method. So we imagine the boxing of the items are like a two-order polynomial function, and this function will reach its minimum value while the sum of the item weight is equal to the capacity. By changing the relationship between this A and B, so we can reach different capacity by a group of Hamiltonian by solving the ground state of a group of Hamiltonian. So also use a standard transformation, we can transfer and map into the quantum circuit spaces. So the relation we control is like this. So K is the K step size we are trying to explore. And here is the process of how the bin packing problem we are trying to solve the solution we get. So first we use the quantum circuits to generate the solutions. And next, by classical computer, we need to select from all the solutions out of these feasible solutions. As long as we have these feasible solutions, we need to, so this is the solution for single bins, and we need to combine all these solutions to get the minimal bins to pack all of the items in the box. Here are the four ansatz we use. As we explained before, this is the traditional QAOA, and this is DC-QAOA, which add a CD term at the end. And next, this is the CD-inspired ansatz, which only require the CD terms and the Hadamard gates to prepare the eigenstate of the initial Hamiltonian. Somehow we find CD inspired and thus is didn't explore enough Hilbert space, so we propose the mixed Hamiltonian plus CD terms to explore just enough Hilbert space and also get the feasible solutions we want. So here's the result. As in the shadowed area, I highlight the infeasible solutions gained by the different ansatz, these four ansatz. So the parameters I choose is this k step size and the iteration numbers. As for the iteration numbers, the more you iterate, the more times you execute the quantum circuits. And for the k step size, the larger the k step size is, the less you measure. So the ideal combination of these is that the less iterations and the larger the k step size is the ideal situation we want. And to analyze the performance of these four ansatz, we can see that for ansatz VCD, when we increase the iteration number, the number of feasible solutions does not lose. Somehow the QAOA will lose the information of the feasible solutions. And also, during the iteration, the infeasible solutions will decrease for the CD-assisted answers. And for k-step size, we can see that QAOA perform really bad at large k-step size, which means that it requires more measurement than the CD-assisted answers. And this is the solution for only single beans. And here we show the result for the last step when we combine all the solutions to obtain the minimal number of beans. So we repeat it for 10 instances and get the following result. I think all the answers can get the correct minimal beans, but somehow the number of solutions are different. The CD mixer and the DC-QAOA can always get the largest number of the solution. So we have these two conclusions. VQ like DC-QAOA can solve these NP-hard problems like bin packing. And also among all instances, answers with CD and assisted can get the minimal number of bins with the most solution numbers. So this is the next example I want to show you, which is quite exciting, quantum chemistry. So the task of this project is to estimate the ground state energy of molecule system. But the problem is that when you increase the atom in the system, the complexity of the problem will become dramatically large. But let's start with dealing the Hamiltonian first. So the total Hamiltonian, which consists of the kinetic energy of the nuclear kinetic energy of the electron and the interaction between them, and also the repulsion between the two electrons. This is so hard to solve, so that's why Born-Oppenheim approximation was introduced, so that we can separate the wave function between the electrons and the nuclear. So the next step is only to solve the electron Hamiltonian. And with Hartree-Fock approximation involved, we can transform this into second quantization basis. But the coefficients Hij, Gij, Kl are defined in this way, which involves the molecular orbitals. So here's the things we care. The molecular orbitals has two like features. The first one is point symmetry. The second one is CAS SEF. So as for the point symmetry, we need to know like the following details. The molecular orbital has the symmetry point, which is defined in a mathematical way, which so the orbital has some symmetry elements like mirror plane, the symmetry axis. If you apply these symmetry elements onto the molecular orbital, it will satisfy some group rules, which makes them a group. And in quantum circuit spaces, we only care about the Boolean group, as the computation is based on the binary computation. So as long as we know how the point symmetry, how the molecule belong to the point symmetry, we can decide which qubits can be removed from the mapping. And for the CASSCF, which is called complete active space, self-consistent field, which mentioned that for the molecular orbitals, we can divide this active space into 3 classes. The first one is the core orbital, which is always occupied by the two electrons, and the active orbitals is occupied by 0 or 1 or 2 electrons, and the external orbitals will never be occupied. So by choosing the active space we are learning, we can reduce the number of qubits so that we don't waste the quantum resources on useless mapping. So here's the result we get. We want to show how we get the ground state energy of this SM molecule. First, we need to take a look at this number of qubits it required. So originally, this SM required 28 qubits, but after symmetry, it only takes 24. And when we choosing the active opto, only 4 qubits is needed to perform the quantum chemistry task. And we compare our result with the standard UCT-SD ansatz, and FCI is kind of obtained from classical method and is treated as the exact result. So this 4CD is obtained from the first order nested commutator. And we can see that the Hamiltonian for SM is written in this way only takes like 56 terms. Compared to the original 28 qubits, it's a dramatic decrease. And we can see that compared to UCC SD ansatz error, the CD ansatz error are kind of remain under the chemical accuracy, which is the ideal result we want to see. So next, I want to show you some variants of the DC-QAOA, which is also popular topics. The biased field DC-QAOA, it will add local field to the mixed Hamiltonian. Every time you are trying to optimize the circuits, it will adapt to a new mixed Hamiltonian. And also the meta-learning DC-QAOA, it combines the machine learning method to trying to choose a better initial parameter so that you can save the iteration process while you are actually doing DC-QAOA. And CD-inspired ansatz, I already shown from the compare of these 4 ansatz, which says that sometimes you only need the CD terms to perform the evolution because of this impulse region theory. So after looking at these 3 examples, it's clear that this shortcuts to adiabaticity and the CD terms can benefit the calculation of the MaxCut, bin packing, and quantum chemistry problem. So also DC-QAOA, it has the flexibility to apply to many systems and introduce arbitrary interactions. So the future work I want to explore maybe is the buried plateau problem, which is the key limitation of the VQA. So the parameters may not move much on the cost landscape, and this is unexplored field in the DC-QAOA. And also the tensor network can largely reduce the quantum resources, which can improve the scalability of the DC-QAOA. As for the quantum chemistry, I want to explore maybe the possible implementation like this maybe in photon basis or any experiment in mental implication. So lastly, I want to thank all of these core authors we collaborate 喜晨 Gloria Bladeno, 月班嘉亮. These four are all from ICMM and the group I belong. Also, Yongchen Ding, Sebastian, they are from the University of Basque Country, and also Goshik and Kanab, and also Man Hong from the Chinese Quantum Academy, and Alice from Barcelona. Thank you very much for your attention, and my talk is over now.
Okay, thank you so much, Ruoqian. Thanks for the very nice talk. I would like now to open the turn for questions. If you have anything to say, to ask, just go ahead now.
Mhm.
Maybe if there are no questions right now, I wanted to ask something regarding this DC-QAOA algorithm.
Mhm.
Do you, or could it be combined with some like worm star techniques that use like classical heuristics or
Yeah.
something like that to initialize the parameters and make it like more smooth or more optimal?
Yeah. Actually, the idea you mentioned is more or less similar with this meta learning DCQA. I I also tried with warm start QA. It's really worked well. So any method that may improve the initial parameters will help this QA, I think.
Okay, and do you have like any comparison of how like the difference in scaling or in performance is with those techniques?
Ah, so by now we didn't have because we are more focusing on uh, dealing with the specific problems, and but we are taking considering to like considering to compare because as DCQA is become more and more like uh, explored, we want to like sort of summary how it can be combined with the existing method.
Okay, right. Thank you so much. Anyone else wants to ask some question? Okay, if not, let's just thank Ruoqian for this talk. Thank you so much, and hope to see you in
Thank
next
you.
seminars, listener.
Thank you. Thank you
Bye.
very much.